morning. When we run a hypothesis test on two groups, sometimes it's called a two-group t-test. We could do a Z, we could do a t-test for two groups t-test, something like that. We sometimes do or want to do what we called a paired sample. A paired sample has a one-to-one relationship. X sub 1, y sub 1, x sub 2, y sub 2, x sub 3, y sub 3. Sometimes this is important when we do medical studies and we want to do one patient versus another patient. Sometimes we do this on a student-by-student basis, and there is always some sort of pairing or some rationalization for having done this. In the case that we have in front of us today, this restaurant, ostensibly we have something like, Friday, Saturday, Sunday, Monday, Tuesday, Wednesday, Thursday, Friday. And so what we have here is a pairing where the sales of restaurant, we'll call these sales, the sales of restaurant 1 and the sales of restaurant 2 are related somehow. And these guys are related because they're on the same day. And as you could probably guess from a restaurant, there are days when the restaurants do better. Fridays and Saturdays are good. Maybe Thursdays, Fridays, and Saturdays are good, right? And so you can kind of see in the numbers that this is a good day, this is a good day, this is a good day. Some of these others are good days, and that they kind of parallel, the days when there's higher activity. So instead of taking, say, X bar for this guy and a Y bar from this one and the two averages, we want to say, hey, wait a minute, there's a relationship on this day, and there's a relationship on this day, and there's a relationship on Friday and Saturday, because Friday and Saturday are the days that restaurants get more activity. So these guys are related, these guys are related, these two guys are related, these two guys are related. And instead of just taking simple averages to try to figure out where we are, we can pair up those two restaurants. And so what we want to do here is take R sub 1. I don't want to do this in red. Let me do it in white. I can take R sub 1 minus R sub 2, restaurant 1. I'm going to take this. I'm going to take this guy, and I'm going to subtract this guy. And then I'm going to get, I don't want to do that in capitals. I'm going to do R sub 1 minus restaurant sub 2 on any particular day, and I'm going to get R sub D, where D means the difference between restaurant 1 and restaurant 2. And every time you hear difference in mathematics, you should be thinking subtraction, right? So what is the difference? R1 minus R2 is equal to the difference, right? No big surprise there. So that's what this little d means right here. It means the difference between R sub 1 and R sub 2. And we could turn around and then just put it here, R sub D, right? And then this guy's going to be negative 2066 or something, but through the magic of mathematics, we kind of have it already. I have it right here. And so I'm going to bring this up here. There. Well, you get the point. There. Well, you get the point. This guy, restaurant 1 minus restaurant 2, gives me that difference, right? And then on day 2, this guy minus this guy gives me that difference. And the same thing, restaurant, on each day I subtract one from the other and I get this R sub D. And again, R sub D really means the difference between the two restaurants at that particular day. Or really, it's the particular observation pairing. So it could be two students, it could be 2 days, it could be to anything that we take them observation by observation. Let's say we had two classrooms where the students were arranged in terms of height, right? And we could take the difference between the two heights of students, and these two would be a pair, these two would be a pair, these two would be a pair, and these two would be a pair. It's kind of unfair to take this big, tall person and compare them against this little guy over here. We get this huge difference. And so pairing, you know, y sub 1, y sub 2, y sub 3, y sub 4 with x sub 1, x sub 2, x sub 3, x sub 4 is a more, see, again, these two are a pair, these two are a pair, these two are a pair, these two are a pair. It's a more reasonable way to find difference when we have some sort of structural pairing. And so that's all we're doing here. We're saying that there's a relationship between day 1 and day 1 for restaurant 1 and restaurant 2. That's what we're doing. And we're going to call this the difference, R sub D. And once we have this, we can make a couple of other calculations. Okay? Once we have this, what we want to do is we want to look at this group only. Okay? Once you calculate R sub D, keep these two guys over on the side for future reference, but we're really just, you know, covering, I don't know how to do this with the pen, but you can kind of forget about all of this and you can forget all about this, and all I care about is this R difference. As a matter of fact, once you make that calculation, you can bring out that difference over here and treat it like a univariate, right? One variable. Once you have this one variable, we can treat it like all sorts of stuff. We want to know the x bar sub d, right? We want to know sigma. It's an S, right? Because we've taken a sample, S sub d, right? We want to know n sub d. And what else do we want to know? I think that's it. Yeah, I think that's basically all we really need. And then we can just calculate these, right? Like we always have. What is x sub d? It is the average of all of this stuff. And looking at the example that we're working, x sub d is negative 1280. The average of the paired differences is negative 1280, right? This guy is 434.3. And the total number of observations is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And total number of observations is 10. Now, I don't want to confuse you with what's going to happen next, but what's going to happen next is we have a small number of observations, so we're probably going to do a t. You can do degrees of freedom sub d, which is equal to n minus 1, and that's equal to 9. So we might need that in the future. It's not a bad idea just to grab it real quick. Again, the biggest difference between this particular two sample test and the ones that we have before is that in a sense you're converting this observation sub 1 and this observation sub 2, or this sample set 1 and this sample set 2, and you're converting it into a singular variable. We're converting this into basically a univariate instead of a multivariate by subtracting the paired differences between them. Okay? Once you have this done and you have created the difference, then you can set it aside and don't allow that to confuse you. And now you're back to a univariate hypothesis test, right? Which we've already done. So let's do them real quick as long as we're here. We'll return back to this in a minute. Let me step outside. Step number 1. I'll do this in white. Step number 1, hypothesis in English. My hypothesis, H sub 1, is that there is a difference in the average sales between the two ones. So, right, there is a difference between the two restaurants. H sub 0, there is no, right, we're already thinking about equal signs here. There is no difference between blah, 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 blah. right? We're already thinking equal. So looks like an equal sign, and this kind of already looks like a not equal sign. Number 2, appropriate statistical measure. We're going to use mu sub d. This is very important. We are going to use the average difference between restaurant sub 1 and restaurant sub 2. Okay? Again, we have converted. We're not doing R1, R2, X bar, difference between yada, yada, yada. We've already taken the difference. We're converting this to a univariate, a single variable. And that single variable is the difference, or the average difference, or the average of the differences. Okay? So in this paired sample, in a paired sample type of problem, we're looking for mu sub d, right? 3. What is 3? One-sided or two-sided? One-sided or two-sided? Well, we don't care that one is bigger than the other. We only care that they are different. So I don't care if it's greater or lower than. So this is a two-sided test. 4, hypothesis in mathematics. H sub 1 means that mu sub d, don't forget your sub d, is different, not the same. There is a difference means that they are not the same as 0. Why 0? Because if I were to take the difference, and you can remember this from one of the non-paired practice problems, mu sub 1 minus mu sub 2 equals to 0 means that these two guys are the same. Anything that's not 0 means that they're different, right? So if I were to turn around and say these are not the same, then these have to be different. Don't care which one's bigger, don't care which one's smaller. All I want to know is that the manager of one of the restaurants is not as good as the manager at the other. I don't care which is which. I just want to know if there's a difference. Okay, which means that H sub 0 is that the differences between them are 0, equal sign, right? 5 is alpha. Have we specified an alpha? We have not. Let's do that now. Alpha is equal to 0.01. If you're doing this out of a textbook, you should be able to specify alpha. If you're doing this on your own, you are the one who gets to specify alpha. You get to select or specify the level of the test. Number 6, statistic. What stat are we going to do? Z versus T versus chi-squared versus whatever else you want to use. In this case, we think that things are normal, but we don't know if they're normal. So is it normally distributed? We don't know. We don't know, can't assume, right? Do we know sigma? We do not know sigma. We know S, right? We have not calculated the standard deviation of the population. We have calculated the standard deviation of the sample, so we don't know that. Do we have more than 30 observations? No, we don't. Since we said we don't know, we don't know, we don't know, or no, 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 then we have to deal with an approximation of normal, and that means we're doing a t distribution. Okay, okay, that's easy enough. 7, determine the critical value. At this point, you know, we're going back to critical value. At this point, it's a univariate example, right? Here's our thing. There's our normal distribution. We've got mu in the middle here somewhere, which is technically 0. 1, 2, 3 standard deviations over there. 1, 2, 3 standard deviations over here. Alpha is equal to 0.01. One tail or two tail? This is a two-tail test, right? Divided by 2 equals 0.005. So out here somewhere, the area under this curve is 0.005. And out here somewhere, the area under this curve is 0.005. They add up together to 0.01, which means that the area under this curve is 0.99, or 99% is in the middle. And then we split 1% on the right tail, and we split 1% on the left tail. So that looks pretty good. That looks pretty good. And let's go ahead and draw our lines. We can actually use this. If we come left of my critical values here, we're going to reject, we're going to reject the null. If we come right of this one, we're going to reject the null. And if not, in the middle, we will fail to reject the null. We haven't actually calculated our critical values. Let's do that now by bringing in a t-distribution table. Let me bring that in over here. And there is our t-distribution table. Let me put this off on the side. Let's do this over here in its own space. There's our t-distribution. So you go to the back of the book or you look this up on the internet. And we know that we are using t, that alpha is equal to 0.01. So this looks good, right? No, that does not look good. Because alpha, I don't want to use red, because alpha is equal to 0.01, but we have a two-tailed test. So that's got to get divided by 2. We're looking for 0.005, right? Sometimes, kind of sidebar, sometimes I get confused when we use the third decimal place here. Right, because it's not 0.01, it's 0.10 and the 0.010. It's the same thing. Don't get confused with the third decimal. It's very helpful when you get to the two-tailed test and you have to divide. So it's not 0.01, even though alpha is equal to 0.01. It's a two-tailed test, so it's not this one. It's this one, 0.005. And also, we're looking at degrees of freedom, right, which is n minus 1. We've already calculated that that's going to be 9. And so we're going to come down to degrees of freedom 9, and we have these two. And where they meet is our critical value. Critical value of 3.250. So then we come back out here and we see that our critical value is, whatever this line is here, 3.250 is our t. 3.250 is our t. Obviously this one is negative and the other one's negative because our mu is always 0. Negative, and the other one is positive because our mu is 0. And that sets up our critical value tables. Matter of fact, this is a good chart. We're going to keep this and we're just going to use it again. Number 8 is calculate our value, or calculate our stat, you get the point. And the great thing about a paired difference is that we go back to a more simplistic. Z is not what I want. I want T sub D is equal to X bar D minus mu sub D over S sub D over the square root of n sub d. And what we really love about this is that if I were to erase, not what I wanted, if I were to erase the d's, then this is a basic t, oh, let me erase this one as well. Then this is just the way we calculate t. Again, this is a univariate or one variable t calculation, right? We are turning around and putting d's on here because we're saying, hey, don't forget that when we started this calculation way back when, we did it by taking the difference between the two groups. That's all we're saying. That's all we're saying. But for mathematical, logistical mathematical purposes, for calculation purposes, this is just a simple old t distribution calculation where we can do plug and play numbers. If you go back to our plug and play numbers, you can see, we're just going to plug in the stuff that we had before. So negative 1280 minus 0. Why 0? Because we're making this assumption that the difference will be 0, right? Over the standard deviation of the sample, which is 434.3 divided by the square root of 10. Remember, this is n, not degrees of freedom. Okay? Make sure you do not confuse degrees of freedom with n. Get out of there. Oops. 10. Right? And at this point, this is just mathematical calculation. There should not be a whole lot of confusion here. And you should get something that looks like negative 9.087 or close. Step number 9, make a decision. Let me zoom back out. Step number 9, make a decision. Do we reject or not reject the null hypothesis? Negative 9.08. Negative 9.08 is going to be over here somewhere. Let me do this in a different color. Negative 9.08 is going to be way out there. We therefore are going to reject the null hypothesis. Let's be patient. This decision is to reject the null hypothesis. 10 is my conclusion. Let's go ahead, as long as we're down here, to restate our hypotheses. My hypothesis is that there is a difference between the restaurants. So the null hypothesis is there is no difference, right? Noting that this is there is a difference means, that one, and that there is no difference, don't get confused here, means our equal sign. Okay, there is a difference, there is no difference. One or the other, we have decided to reject the null hypothesis. Therefore, we are going to accept this one at alpha equals 0.01. Given an alpha of 0.01, or given a confidence interval of 99%, we can state that there is a difference with sales between the two restaurants. Okay, and let me return, so that's your conclusion. That's your conclusion, that's the whole thing, and then we're done. Let me return back to the original data. So now you're trying to make a decision between firing one of the two managers or whatever, and you're looking at this data. The other manager is going to turn around and say, the manager of restaurant 1, manager sub 1, turns around and says, look, we do just as well as they do, except that on these days, these 2 days, they're getting, he's doing better than I am, sure, because on these 2 days they get weddings or they get rentals, but I don't have that rental space. That's not my fault. Well, since we did paired differences and we subtracted this guy from that guy and this guy from that guy, and we looked at what those patterns looked like over time, you can turn around and say, yes, he has more space. Yes, he gets these other rentals, but even so, there's still a difference between the sales of the two restaurants, and then you as owner of the restaurants can make a decision about a more informed decision about whether or not you want to fire these guys or keep them or whatever else it is that you're trying to do. I hope that was helpful. I'll see you in class or on the internet.